I would like to invite our first platinum sponsor, which is my company Kyland, to share with you some results of 1588 solutions in power. I would like to invite Ben 王斌。接下来我想邀请我们公司作为一个白金赞助商，跟大家分享一下我们在1588的一些成果。
Good morning, everyone. My name is Ben Huang. Today we will show the live demo, the 1588 application power. Everybody knows, recent year, China has built up over 1,000 new smart substations for each year. Compare the traditional substation, the smart substation, the time synchronization is more important. In general, in general, we divide into the smart substation in 3 layers. One is the substation layer. The second is the bay layer. The third is the process layer. So different layer has a different time accuracy requirements. For substation layer, we mostly use NTP for time synchronization. The time accuracy is several milliseconds. For the bay layer, we mostly use RB, or it's also some substation use 1588. The accuracy, the requirements is 1 millisecond. It's better than 1 millisecond. For the process layer, we use lots of the merging units, all the sampling value from here. For the power, for each second, the sampling value rate is 4,000 times per second. So we must keep the time series, all the mergers as a time synchronization. Sometimes, some IEDs, the sampling data from different merger units. So, if you lose the time synchronization, the IED, especially the protection relays, has get a big trouble. Maybe has misoperation for the substation breaker. The power system will become more unstable. So we must keep the time synchronization here. So when the process passes, the time accuracy is, the requirements is better than the 1 microsecond. So sometimes we use the nanosecond about this. Okay, this is parameters for requirements of the power. We will go through the detail. So now, in China, we have some applications in the smart substation. One is in the Yan'an 330 kV substation. This substation uses all the IEDs and bay controllers, or the merging units use 158 for the time synchronization. So it's a big substation in China. This is for the China state grid, the Shanxi province. So you can see lots of the switches, clocks in there. So it has some more the 1588 power application in China, especially in the Eurogrid transmission, the substation. So all the Eurogrid, the substation use 1588. The day after tomorrow, Mr. Alejandro will do the detail about this one. So for the challenge to the resolve in the smart substation, first we will have to keep the more time synchronization stable. That's why we use multi-source selection and redundant. So in China, we use GPS and Beidou, Chinese GPS that we call Beidou. It's also use grounding. Now China has a standard use E1 as a frequency for the grounding the time. So we must have the algorithm for calculate, which is the best one for the time synchronization. We must keep the stable, otherwise merging units has a big trouble. The second, we'll have the equipment to test the time accuracy, especially about the IEP's time performance. We not only test the clock, such as IEEE 1588, it's also we test the measure, the time delay of the Ethernet package transmission time delay. So this is more works in the substation. Also, in the substation, we have to real-time monitor the time difference. If some just a machine from merging units, if some merging units lose the time synchronization, maybe big trouble. So we have the real-time monitor this time synchronization performance. We call it TMS. Also in substation, we must have the interoperating, such as a time server, Ethernet switch, and some IDs. We must keep all the IDs time synchronization. Capability. So we have a different profiles defined. That's why in the Europe we have to keep some ground the source from the communication side. So we will convert the communication Wi-Fi communication profile to the power. So it's also new network knowledge has come up, just HSR, PRP. So we have to put into the new application in the substation. Today we will shoot the lab demo. This will first of all see the time synchronization. Secondly, we will show how to measure test the time accuracy. The third, you can see the TMS function side. So we will synchronize this ID. It also can automatically monitor the time performance. So this is today we will show that. After demo, I and my team will be there to answer your question. So now I will invite Julie will do the demo.
Okay, thanks Ben. Now, thanks Ben for the presentation, and now I think it's the time for real stuff. I'd like to show some real stuff here. Okay, first of all, I'd like to introduce the setup of the demonstration today. So in the picture here, you can see that in today's demonstration, we have 2 time servers, which is already synced with the GNSS signal and also working a redundant mode. And now we have 3 Ethernet switches from different vendors, which all works in layer 2 peer-to-peer. And we have 2 different protection relays. And one protection relay is synced with IEEE1588. And the other protection relay is synced with LB, which is converted by a time converter from IEEE1588 to LB. We're using a time tester to test all different time signals in the system to check the accuracy of the system. And also we are using a TMS system to monitor the whole time system. Okay, for this joint live demonstration, thanks to the following contributors here. Okay. first we have the time server from Nari, and the second time server here from Kyland. And we have the DGX1. This is the data analyzer for TMS system. And the three switches are from the first one, Kyland, Sifang 3028 GPT. The second one, Nari PCS. The third one is from the Shiji system. This is the protection relay from Schweizer 701A, and the device here is the clock converter, PDC 1000. And the last one, we have the protection relays. This one is from the Sifang company. And then, this is a tester we are using today, EPD100. You can see that there are multiple different channels here. This one is for testing of IEEE1588, and this one are for PPX, for everything testing here. Okay, so let's move on to our first demonstration. First demonstration, I want to check the grandmaster status and to see how the PMC works between the two redundant time server here. And in the screen, you can check that they are using two different priorities. So now the PDS30 has a higher priority with 100, which means that now in the switch we can check the grandmaster. The grandmaster should be the PDS30. And okay, so now we check first. This one is the settings of the PDS30, and now the priority is 100. And then we go to check the grandmaster. We can check in the GP switch, the grandmaster clock ID is this one. This is the clock ID from PDS30. And later on, when we switch over, we can also check the grandmaster identity should be a different one. And now, in this system, we go to, in this setup, we go to check the PDB accuracy. And the first one, we check the PDB accuracy via one hop via the Kyland switch here. So we run a test of IEEE1588 in the time tester. Okay, so here you can see the results here. The results here, we can see the grandmaster clock accuracy, and right now this shows the real-time offset of the PDB via one hop of Kyland switch. And then for the next demonstration here, we change the tester cables to the second switch, the Nari switch, and to see the PDB accuracy via two hops of switches in the system. Now you can see the offset of the accuracy via two hops of the switch. Okay, so how about the three hops of the switch? How about the performance of three hops of the switch? And then we also change the test cable to the third switch there, and start the IEEE1588 start with the IEEE1588 test. Okay. Okay, this one you can tell that is a bigger one, but still you can tell that this is for the mean value. It is quite stable, and which also with a very small deviation, which means that this one is maybe not calculated, but the performance is quite stable here with the variation here. So we have two different end devices here. One is the Sifang protection relay. This one is synced with direct IEEE1588. So, but it also has a PPS output. So we can check the PPS output sync accuracy through this one to check how the Sifang relay is actually synced with IEEE1588. Okay. In the screen, this shows the PPS output of the Sifang relay after the time synchronization using IEEE1588. So, since we are using a clock converter, so we can also use the time tester to check the output of the error B from the clock converter. Now we start the error B test here. And from the screen, we can not only check the offset, the time offset of the error B, but also these are all the decode information of the error B information here. Now goes to TMS. Since we know that for time synchronization via network, it is very difficult to tell actually how the end device is really sync with the grandmaster or not. Sometimes we use SNMP or MMS report to get the self-report information from the end devices. But this kind of information is usually based on predictable events. But for those unpredictable events which cause the out of sync events, sometimes we have no measurement for these end devices. So in our TMS solution, we are using a GPS trigger module, and this GPS trigger module is already synced with the grandmaster clock in the system, and publish the boost messages into the system. So anyone who receives this, who subscribe this boost information can send out the MMS report with SOE information inside. So we are using a data analyzer to concentrate and analyze all this MMS report from these end devices, and we can use an HMI through this data analyzer to track the node time in the system. And that's how this TMS works. And then this is how the TMS HMI really looks now when it comes to see in this kind of real working system. In this TMS system, you can see there are different areas. This area is for the topology, and this area here we check. This is the real time deviation of different nodes. We have the master clock nodes, and we have the switch nodes, and we also have the end nodes like this, like the protection relays. And here we show the histogram of all this kind of nodes time in the system, those times deviation in the system. And in this also topology, we can see that here, all this information here shows the real time. Since we are using a periodically trigger based on 1 minute, so here we can shows the UTC time based on the hour, and minute. Okay. So it goes on to the next one. So here we're going to do a switch over between different grandmaster. First, we'd like to run the PPS test through the Sifang relay, and we like to check the performance during this kind of grandmaster switch over. And then now we change the parameter of the priority one in Kyland clock. We change the priority one from 100 to 200. Now, since the Nari's clock already run is 128, based on the BMC algorithm, the grandmaster clock should be changed to Nari's clock. So we can see that the clock identity, the grandmaster clock identity has already changed to the Nari's clock. And then we go back to the PPS test here. Okay. So this test, since it starts before we switch over, so this shows the this time shows the current offset, and this one is the mean time, and also this one is the deviation during the whole switchover process. Last one but not least, we like to see what will happen if the Schweizer protection relay is out of sync. So we will kind of pull out the Arabic input of the Schweizer relay and check through the TMS system what will happen. So please roll. Okay, I think since for the end devices, the out of sync will take some time, since some end device may have the holdover function, and also so that's will take some minutes to go to check. Okay, I think it's still in the holdover process. Okay, so I think we have enough time here now. So for this out of sync event, I think it will take some time. If you're really quite interested in this one, all these devices will be here, and we will please enjoy the next time and to check personally here if you are quite interested. Okay, I think it's still synchronized. So, okay, for the summary of today's live demonstration, the first one, I think we have checked the sync accuracy. So I think the sync accuracy is quite good enough for the 1 microsecond application which asks for some power applications. And the second one, we have the Arabic conversion. This kind of solution is good for the system which need to sync the legacy devices which support Arabic in the IEEE1588 network. So third one, for the redundant grandmaster clock, we see that the end devices perform quite smooth, quite good in the smooth, which shows a smooth switch over, which makes this system more reliable. For the TMS, the TMS provides a solution for no-time tracking, which is quite beneficial for end users' maintenance and management for the system. So what we are expecting in the future from the last 3 days clock fest, we're expecting more conformance tests for the standards for different profiles. Then we are expecting more interoperability tests to make sure devices from different vendors can work alright with each other. And the third one, I think, is align the standards, because right now we have profiles which is called the power profile, but we are also having the power utility file. So we are expecting more aligned standards, so the vendors can look up to. So for time management, this is also a key issue for the end device for end users. And the last one, I think cybersecurity is always not good enough to talk much more about the cybersecurity in the system. So that's all for my presentation today. And of course, if you are interested, and we are very glad to show you some more tests in the demonstration step here. Thank you very much.